Bring up our spreadsheet. Okay, so as I promised, I'll go over anything you want to go over in Chapter 1. Someone emailed me 3 comments that they want to go over. And the first one was how the gas gradient has been calculated. Gradient and density are related by the units conversion factor 12 inches per foot squared. And that can change you from pounds per cubic feet to PSI per linear foot. So if you have a density and you want to know what that gradient is, and basically we're talking about, I'll use the term fluid density because it doesn't matter if it's a solid density, but if you have a fluid density, and so let's say you have fluid in the wellbore, if you know its pressure at 2 different points or 2 different depths, and it's linear, then you have a gradient. You can multiply that gradient times 144 to get its density, and vice versa. If you knew the density, you could divide by 144 and get the gradient. My units here are pounds per cubic feet for density, and PSI, or pounds per square inch, per linear foot. How much the pressure changes each foot we go deeper. This is real important if you're a scuba diver, right? Because the deeper you go, at some point in time, the pressure is such that you have to have some kind of mechanical device, otherwise it'll squish you. The pressure of the water as you go deeper in the ocean. Okay, who asked that question? Okay, does that answer your question completely?
Yeah, I understand the concept, but actually the values those were calculated in the sheet. I didn't follow the steps. I would appreciate if you just repeat.
Do you see where I calculated density on the sheet? Here, right here.
Yeah.
Let me zoom in. Okay, so I actually have a little function, because I use the density of water all the time. If I'm going to use it, I mean, I can remember 62.4, but sometimes I want it to more significant digits, so I have a little function that gives it to me in more and more significant digits. Okay, so that's the density of water at atmospheric conditions. Now to get 0.433, that's a number that if you're in this country you hear all the time. That's the gradient of fresh water, 0.433 psi per foot. And you can see in my calculation line, all I did is take the cell above it and divide by 144. So if you had a pressure bomb that you lowered in the hole and you hit a gas gradient, then you hit a liquid gradient and it got heavier, and you knew that liquid gradient was 0.3 psi per foot, and I asked you what the density was, you just take 0.3 psi per foot and multiply it by 144, and you'd say its density is 43.2. Now you could also say that it's, let's say it's an oil. We know it's an oil. We could say it's, we can't say that. We can't say what its specific gravity is compared to liquid, because in order to convert that to API, we would have to know its specific gravity at atmospheric conditions. We just know its density at temperature and pressure. Now how do we take, for gas reservoir engineering, how could we take a density at reservoir conditions and express it as a density at atmospheric conditions? How could we? Can we do that?
Using our correlations backwards? Using the correlations that we've...
It's not really a correlation. It's the reservoir volume factor, right? I did E sub G, which is 1 over B sub G. So B sub G is the reservoir volume per standard cubic volume. Density is mass per volume. So you have to be careful there because you want to watch your units, because I think you'd want to get, I think the term is specific volume, which is the reciprocal of density. Then you can multiply. Otherwise, you'd have to, but you have to reciprocate density to get the right units to change the volume per volume. Because the mass is going to be the same. The volume is going to be different. B sub G, the formation volume factor, can convert that volume of gas at reservoir conditions to standard conditions. So actually, if you knew the density, let's say this, if you knew the gradient at reservoir conditions, then you could determine the density at reservoir conditions, and you could determine its density at atmospheric conditions, and that density compared to the density of air would give you the specific gravity. That wouldn't be a normal way you would get gas gravity, but you could get it that way. But think of it this way, if you knew the specific gas gravity, and you calculated or related that in terms of density by multiplying by the density of air, and which don't we have the wherewithal to do that. We have a gas gravity in our example, don't we? Where is it? Higher? Over? Oh yeah, it's 1.087. Now, I think I have a little VV function for the density of air. You don't need these. See, I know what the density of air is. It doesn't take any arguments because it just is going to give me the number. It's 0.00 something. 0.0. That's the density of air. So if I want to know the density of this specific gas gravity, this is the density of air. So what am I going to do with those two numbers to get the density of that gas gravity?
You're going to multiply it by
Multiply those two numbers together. Okay. Question 2 was, please discuss the steps for calculating pseudopressure.
I just asked something about this. So we're going on with it.
Sure. You guys got to speak up though. This thing hums at me.
I just want to make sure I understand it right. So if we have pressure and depth on a chart, we would need it to be linear in order to get a gradient.
Let's see, I think this is on. A lot of times you'll see a gas gradient in an oil well, then it'll hit liquid level. That liquid level is real easy to find, lowering a pressure bomb in a hole, raising it, getting it back out, and getting pressure versus depth. And we usually plot this the way it physically looks. So here's our depth at 0, and here's our depth. I think in this problem we got 8,000 feet. Okay. If it's linear, it makes the problem easy.
Yeah.
It may not be linear. And with gas, we typically get kind of a subtle curve. But that doesn't mean that we couldn't take the tangent anywhere and get the gradient at that point. Just the way I just did it, just eyeball it. But I made my statement a little bit simplistic when I said if you have a linear trend, then bam, you do have your gradient.
Correct.
If you have a curve, then it's a little bit harder, but the gradient would be the tangent of that pressure depth plot anywhere. The way to do it is do a polynomial fit of it and then take the first derivative and you should have the slope everywhere.
Dr. Khaled, since your pressure and your temperature are going to lower from reservoir to surface, that's going to have an effect on the density and thus the gradient, right? Is it significant enough that we would want to do what you just suggested?
You'd want to do it. When you lower a pressure bomb in the hole, there's 3 tracks. There's 4 tracks. They'll show time, and this will just be clock time, just like on your watch. Okay, that just shows you where you are, how long the job was, and stuff like that. Then you'd have pressure, and you'd have temp. And so if I wanted to calculate the density of the fluid, let's say this is where my formation was. So right across from my formation, I'd be interested in that temperature, which, you know, maybe I've got a lot of rat tail in my well, so I lower it through my formation and even deeper. Maybe I'm interested in some other zones too, because another zone may have a different temperature or pressure regime. But I should be able to, and I don't, you know, you could have an auxiliary scale on here, but your temperature would increase as well as your pressure would increase as
right.
you bomb lowered. So you'd want to know what that temperature was at that point.
Okay.
But in most cases, we only drill our well through our formation. We don't, that costs money to drill well, especially in a developmental well after we've already checked out the lower horizons. Usually it's the bottom hole conditions means the formation conditions. Those are synonymous, but not always. Does that answer your question?
Yes, sir. Thank you.
Yes.
I'm just going to make an assumption here. You said if we have 2 points, when you talk about the gradient, what about the scenario we have more than 2 points at different pressure we have, at different depth we have a particular pressure? What about you give us a scenario where you give us like 4 points? Then how are we going to calculate them to give us one particular gradient? You just assume we have just 2 points. What about we have more than 2 points?
Well, let's say these are the points that are on our table. As a first approximation, you could take 2 points that are closest to your zone of interest, right? And then those 2 points would be approximately the tangent at that point.
Okay, we don't need to consider all the points.
No. Normally I'm interested in the density of the fluid at reservoir temperature and pressure.
So we're just going to look at the closest point that is close to the reservoir condition.
At reservoir conditions, right, yeah. Basically, I don't care too much about what happens between the top and the bottom. I'm interested in the fluid at reservoir conditions and at surface conditions. And my formation volume factor can always convert one to the other.
The question that I posed was in the context of estimating the pressure drop from reservoir to surface.
Yes.
Since that pressure gradient is going to change.
Yes.
Up the well stem because of the differences in pressure and temperature.
Yes.
That's what I'm saying. Can we use an approximation of the gradient using the surface of the reservoir, or is it different enough that we would want to?
Okay, I'll spend the next 5 minutes going over chapter 4,
Never mind.
which we're not going to cover. But it's important to be able to do this density calculation. But what we would do is we would calculate the density at the surface. Okay? We can get that, right?
Mm-hmm.
And let's go down a foot. So if I know the density, I know the gradient. And pretty much we have a geothermal gradient for in any basin. So there's not huge discrepancies. Typically, if you have a bottom hole temperature and a surface temperature, you just do a linear gradient.
Okay.
So at any depth, I know the temperature. So I go down a foot, and I use my gradient to get there to tell me what the pressure is there. But now I have a new pressure
Right.
and a new temperature, so I can calculate a new what?
A new density.
A new density. Because density is a function of pressure, temperature, and composition. And then I can then divide by 144 and calculate a new gradient, go down another foot.
Right.
This technique is called gradient methods. Okay? And then really all that's required is if you divide the well into 10 intervals, you know, you can go 1,000 foot at a time probably and still get a good approximation. And if you bundle this technique up into a Visual Basic program that was a function of n, the number of intervals you break it into, then you'd get a different answer and a different answer, and then as n increases, then eventually you'd get the same answer.
Right.
For using gradient methods. So now I've covered chapter 4.
So for our purposes, though, in what we've talked about, is that a level of trouble that we want to go to?
In industry, you'll have a CAN software thing. Someone could just Google it right now. Bottom hole flowing pressure, bottom hole static pressure calculator on the internet. These types of programs, I used to make that part of this course because it's pretty good engineering physics to do that. But the thing of it is that it doesn't give you any useful thing when you graduate from here, because every company you work for will already have a CAN program to do that for you. So calculating bottom hole pressure and static pressure are easy things to do. But the technique is really what we call gradient methods. And then the only thing that's different between flowing pressures and static pressures is you have to account for friction. And I used to start this course with chapter 1, then go to chapter 4 and spend time on that. But it's just, I think there's good engineering physics and good understanding that can be had by deriving those calculations. But when it's all said and done, I'm not giving you anything that's useful. By doing chapters 6 and 9, I'm trying to give you the tools that when you get data coming in, especially if you're in exploration and production. How many people are going to work for an exploration and production company? Okay. Then transient analysis, that data is going to come in every day. If it's either transient pressure data, typically what you see on multi-frac horizontals are defits. How many people have heard of a defit? Okay, so we'll get to the point where we can look at defits, but this book doesn't really cover defits, but it covers the science behind defits. It's not that much harder to go into defits. And then, yes?
What's a defit?
Diagnostic fracture injection test. Okay, so what they do is they've drilled their vertical and horizontal well, and they've only perforated the toe. And then they pump some water, brine, mud, something in there until they can break the formation. And they're accurately measuring the pressure. And liquid gradients are really much easier to calculate than gas gradients. And the big thing they want to do is see at what pressure they can break the rock, because that has a lot to do with how they're going to design their stimulation treatment, because they're going to pump water and sand. And so the service company that's going to come in there is going to want immediately from that defect test know what it's going to take to break down the rock, so they can get the right size pump and create that kind of pressure. That's just one attribute you can get from a defect. But as we'll see when we get into chapter 6, oftentimes from any pressure test you can get initial reservoir pressure. And so that's a very valuable thing. And sometimes we can get the holy grail. That's permeability. That's the thing that we really would like to get. That's the dynamic aspect of the reservoir rock. Porosity is kind of the static effect. It's storativity. But its ability to flow is permeability. I'd say probably a little less than half the time we can get permeability from a defect, but we should always get the pressure that we can break down the formation. That's critical. That's what the service company wants to know. And oftentimes we can get initial reservoir pressure. That's good for the service company. It's good for me, the reservoir engineer. When I start making my calculations for original gas in place, I need B sub GI. B sub GI is a function of PI. How do I get PI? I can get it from a defect. Okay, MOP, pseudo pressure. Is there a question on that? What's your question?
I missed the steps to calculate the MOP.
You're happy with MOP?
Sorry.
You have a question still about pseudo pressure?
Could you please go to the Excel sheet and see?
I just use the visual basic function. Like all these gas properties, it's a function of pressure, temperature, and composition. What do I have all these numbers in here for? What was I doing? Okay, I was making that graph. Get rid of those. So I looked at some static properties, then I got pseudo pressure, and I invoke the visual basic function M of P. And all these gas properties have the same inputs: pressure, temperature, and composition. Composition entails four members: gas, gravity is the bulk of it, and then the three impurities that are non-hydrocarbon, common non-hydrocarbon impurities. Okay, so it's a number. Usually it's a large number. And I think in this column, I have it as a function of the wrong gas gravity. Okay, for comparison basis, I put it as a function of the wrong gas gravity. And it's different. And then I looked at the delta pseudo pressure, and I looked at the air in delta pseudo pressure, and it's huge. And I emphasize this because there's engineers out there today using the separator gas gravity and not accounting for the liquid content of the oil and tank vapors to calculate their real gas gravity. So it's a point I emphasize in Chapter 1. We have to know that we have a separator out there. Just because you have a gas gravity may not be the gas gravity that's in the reservoir. The error is huge. No one here is going to accept a 41% error in a calculation. Okay, and then on your email it said at PR and P abandonment. Well, I think I went over all that for you. P reservoir and P abandonment. P in the reservoir could be at any time. As you deplete the reservoir pressure declines. So normally I'm just interested in current conditions, bottom hole flowing pressure and initial pressure.
Was pressure abandonment? What is my mind?
We made a rough calculation of abandonment pressure at what, 10% of the depth or something like that. Did we get an abandonment out of the where is our P at abandonment?
I understood how to calculate it, but I mean conceptually.
I guessed it. Okay, conceptually. I've got a reservoir, and it's producing at commercial rates. Let's say it's producing 1 million cubic feet a day. But what's the rate going to be tomorrow?
After we've started to
Deplete it, what's the rate going to do? It's going to go down. At some point down, it gets to a point that its rate times gas price, or its revenue, is exactly the same as what it costs to operate that lease. That's called the economic limit. So there's still gas there, but it's costing me money after that point. You see, if you're operating another kind of business, let's say a restaurant business, just because you lose money this month, you don't quit. Because you might make, maybe the holidays are coming. So you might make more money. But on oil and gas production, if it's declining, and it's done this for 30 years, unless you do something drastic, and maybe you do, maybe you re-stimulate the well, maybe you try to do something to get it back up to rate. But at some point you give up on it.
So the point at which you give up is the pressure abandonment?
Yes. Yeah, but that may not be the flowing pressure, because remember I always show that picture of that vortex toward the well. It's not a straight line.
Will that usually be something you can foresee in the future based on your economics? Like after you do enough depletion curve analysis, or possibly, or at least look at your, like you can say, okay, we know that 4 years from now, we probably won't have enough pressure.
When we finish Chapter 6 and Chapter 9, you'll get a good feel for how we do decline curve analysis, calculate this economic limit, and then tie together that with reservoir engineering. We should be able to figure out how big our reservoir is. We should be able to do a rate forecast, and we should be able to figure out when we get to this economic limit. Then we should know how much cumulative gas we've produced. Well, the cumulative gas produced and the gas originally in place are linearly related with that P over Z curve that I showed last week. So I should be able to, yes, calculate the pressure of abandonment. Do I ever calculate the pressure of abandonment first? No. I usually see what my forecast is going to tell me what my pressure of abandonment is. I just did a guess.
Okay.
I took a gas gradient from my depth and I bumped it by 1.3 to guesstimate how much more than the bottom hole flowing pressure is in the vortex. Just to have some numbers to work with. Yes?
In your analysis, when you, at the end of the day, calculated the pseudo pressure for the abandonment and the original one, you only consider the change in specific gravity at the surface. As that was the only input you adjusted.
Yeah, the only perturbation I made in that right column and in that wrong column was using the wrong gas gravity, the separator gas gravity.
So I'm just assuming maybe there is a distance. Doesn't think temperature or pressure could also make some
Doesn't make nearly as much of an error, right?
compared to this.
Yeah. So not using the right fluid composition is what I have seen engineers make gross errors. If you use 145 degrees instead of 150 degrees as your estimate of bottom hole temperature, then you'll maybe have a 3% error. And I'll tell you why you're always going to be a little low on your reservoir temperature thing is because typically an engineer will get their formation temperature from what? What's lowered in the hole on every well that measures temperature?
Downward gauges. Downward gauges, bottom gauges.
No, we do that occasionally, but I'm talking about every well required by the state. Then they're all stored in the basement at the Oklahoma Geological Survey. A wireline log, okay? Now, they don't dictate what logs have to be run, but all operators run some logs. We talked briefly about like the density log. That's how we're going to get porosity, right? But every one of those logs has to know the temperature because it takes some kind of nuclear measurement and that is sensitive to temperature. So every log that's running the hole, every electric, we nickname those electric logs, although in the early days that's what we did is measure resistivity. That's something we measure. But now we have acoustic and we have density logs and we have spectral gamma ray logs. We have all kinds of logs we run in the hole, and it depends upon what formation that we're interested in producing, which suite of logs best applies for the information that we need. But every single log that runs in the hole has a temperature gauge. And it needs that temperature because when it displays its output, they're all temperature corrected, just like we have to make temperature corrections. So on the cover of any log, how many people have seen a log? It's, you know, an accordion piece of paper, right? Because it stretches way out. And right on the cover it says maximum recorded temperature. Okay? Why is that less than the actual reservoir temperature?
Inside the wellbore.
Pardon?
Because inside the wellbore, and you have like fluid there.
You have fluid there. What about that fluid? What if I left it there for 10 years? Would it give me the right temperature?
Maybe.
Yeah. What if but the thing of it is we've been circulating mud from the surface all the time we're drilling, and right before the service company comes out, we lower the logs. So we're cooling our wellbore. We're cooling the earth near our wellbore because we're circulating a cool fluid. Okay, so our maximum recorded temperature is always going to be less than formation temperature.
But if you have a permanent gauge there,
Permanent gauges are rare. They're expensive. But if you have a permanent, in big fields like Ekofisk in the North Sea or something like that, they probably have permanent bottom hole pressure gauges and bottom hole temperature gauges. Then it's not as big a problem. But when you start producing the reservoir, what happens to the temperature in that gauge? Huh?
reduces.
What?
Reduce.
Yeah, why does it reduce? Expansion of fluids is a endothermic reaction, so it cools it. So it's hard to pinpoint exactly what that temperature is. So typically we use models that match that data, and we can eventually figure out what that temperature is. But again, it's a small error. It's not a 47% error.
So, sorry. I know you said you took the measurement of the 1.09 from the separator 1.
Yeah.
And that is what you have been using. What I'm trying to understand is the specific gravity. You were able to get it from the separator itself at the source.
Yes.
Okay. Now let's assume we're in the field, and we're running all this calculation. The purpose of running this calculation is it to checkmate to be sure that what we measured, the measurement, the specific gravity we measured from our first storage is correct. I think what I'm trying to say is this correlation we're doing now, you're trying to checkmate, doing a pseudo pressure. Are you trying to
No, we're using our surface measurements as givens. Okay, but we have oil in our stock tank that used to be gas, and when it was gas, it took that gas and it made it heavier. We're just trying to figure out how much heavier. And then also those very high ends that are rolling off the stock tank oil to the atmosphere, we call them tank vapors. They're a high gravity. There's a lot different gravity than the separator. We have to account for those also in determining the well stream gas gravity that came up the well. Because that well stream gas gravity is what's in the reservoir. So when I'm calculating Z to get my formation volume factor, when I'm calculating viscosity, when I'm calculating pseudo pressure, anything I'm calculating, I want the composition, the gravity and impurities of the reservoir gas, not of the primary first stage separator gas, even though that's what I'm selling. Yeah.
We showed an example that the gravity of the reservoir fluid was lighter than the gravity of the third stage stock tank vapors. Is that always true?
No.
Okay.
I could change my liquid yield drastically. If I made just playing with the numbers, if I just made my liquid yield higher, my GOR lower, that would bump my well stream gas gravity to be higher than my tank vapors.
Okay, that's helpful.
The only thing that I can tell you for certain is this will always be the lowest number. Because what you've done is you've separated at high pressure and left all the liquids and all the heavier gases behind. So when you add that back in, it's always going to be bigger. So that's always the smallest number. What is the biggest number? What is it? Is it the tank vapors, or is it the well stream gas gravity? Could be either.
Gotcha.
Stock tank.
What did I say?
The stock tank.
Stock tank vapors. Question number 3. How the impact of wrong gas gravity was calculated on the original gas in place. B over G uses Z. That's the only static calculation there. So original gas in place, I don't know why I got, oh yeah, I got them in MCF, and I got them in BCF. And it's only a 1% error. It's going to be the same 1% error in MCF as it is in BCF, right? So I only got a 1% error because B sub, original gas in place is a function of B sub G. And so this is also going to be a 1% error exactly because that's the only thing that is affecting it. Your formation volume factor has a Z in it, supercompressibility factor. Yes.
I just was looking through your these equations you gave us. It's a great gift. I'm not familiar with it, all the VBA, but you have one function in there. It's called pressure, and we were talking about P over Z and calculating the original gas in place, and it looks like it's just an iterative loop where it hones in on Z.
We may not use that in this class. What it does, if you have an analytic function, you can always use the Newton-Raphson iteration. And if you don't have an analytic function, like a Z function, you can always use the secant method, where given two guesses, you can get a third better guess. So that's what that's doing. And what I'm sometimes interested in doing is rapidly getting a couple of points on a P over Z Cume plot, where this is original gas in place. I didn't know I was going to use the board so much, so I wrote my own markers. So this is original gas in place. Given a P over Z at some point, so my manager comes in and says, when this reservoir produces 3 BCF, what will my pressure be? I got 10 seconds to answer it. Well, I've got a linear relationship. I can come right up here and get P over Z.
Right.
And I know that the way you'd normally do this is enter a pressure, calculate a Z, and then plot your P over Z. But what that does is iterate, and that calculates pressure given a P over Z. Probably won't have to use that your entire lesson. If I use it once, I write a program to do it. That way I don't have to spend any time doing it the second time. All done with questions? Yes.
Throughout talking about chapter 1, you've hammered home, and even listened to the recordings from the lectures, that the one thing that you wanted us to grasp was the significance of finding the reservoir gas gravity from surface conditions.
Yes.
Can you comment on that and help us to understand the significance of knowing the reservoir gas gravity as, like, from a business perspective?
Well, let's say you're midstream or downstream, and you're trying to decide whether or not you're going to build a pipeline to somebody that's just drilled a new field. That's a business decision you'll have to make. And it's going to be based on the deliverability of that gas and how much gas is in place. Now, if you are only interested in the original gas in place, I've just shown that maybe you'll end up with only a 1% error using the wrong gas. But the deliverability is going to affect the time it takes to get that. So if you're looking like at a 5-year project versus a 10-year project, that's what kind of error you're going to get with a 40% error in delta pseudopressure when you're calculating the deliverability. Because rate is a function of delta pseudopressure. So you may be off by a factor of 2, approximately, in the life that you calculate. So if your discounted economics won't handle a 10-year life, but only a 5-year life, then you're going to straddle that decision-making point and make the wrong decision. Why don't I move on to chapter 6? And if you think of some more burning questions about chapter 1, we can look at it.
Real quick before we move on. So any of the relationships towards oil, crisp oil, viscosity oil, or the water that's covered in chapter 1, would you like us to have a full handle on that, or just the stuff we focused on?
No. I have in the past, but I want to spend more time on the dynamics. And although every hydrocarbon reservoir does produce gas, it's impossible for it not to. The book is very complete for the situation where you're producing or selling gas from an oil reservoir. Because you have to understand the reservoir is going to hit a bubble point, and it's actually going to start producing more gas. So if you're trying to look at the business decision about how much gas that reservoir is going to come out, you have to understand a lot more. But the complexity that's involved with multi-phase flow in the reservoir, I'm avoiding in this class. You don't have to know everything there is about oil reservoirs just to do gas reservoir engineering calculations. Yeah.
I had one more question. I realized too late into the class that compressibility factor, the Z factor, and compressibility are not the same thing.
Sometimes the Z factor is called the supercompressibility.
Okay.
If you had an ideal gas, what is the equation for compressibility? Huh?
C is equal to 1 upon P.
C is equal to 1 over P. Correct. The compressibility is just the reciprocal of the pressure.
Okay.
Okay. Now for real gas, it's equal to 1 over pressure minus 1 over Z dZ dP. So that is the compressibility. It's a function of Z, and it's a function of the slope of Z as a function of pressure. And so Z is sometimes referred to as the supercompressibility factor, but people don't like to use that word super, so sometimes they just call it the compressibility factor. But it's not compressibility. Compressibility is approximately 1 over pressure. And for an ideal gas, it is equal to 1 over pressure. But I'm glad you brought that up. It's important to know the difference between, just like there's a real gas law and an ideal gas law, there's also an ideal compressibility, because it's just the ideal gas law. You change the pressure, you're gonna your pressure volume relationships are inversely proportional. But since gas doesn't behave ideally, we have to include Z, which is sometimes called the supercompressibility factor. Did you just always say we're just calling it the Z factor? Yep.
I just realized we didn't incorporate viscosity and the compressibility into our calculation.
Did I not calculate viscosity at the wrong and correct?
And then it's not incorporated into the main calculation. Like, doesn't in any way affect the single pressure that is calculated.
Well, yes, it does, indirectly. What do we got here? Pseudopressure is a function of gas viscosity. We're gonna look at a little bit of pseudopressure tonight when we look at chapter 6.
But in the MP function,
This is the MP function.
yeah, if you look at bracketed function there, like if you go,
Hang on, let's go to the book.
Isn't the G the viscosity in this?
I'm not listening. Hang on. Okay, it's in chapter 6. Let's just look at the equation. Equation 621, right here.
What I think he doesn't understand is that in the DEA, it's using the code for viscosity in that function down there, so you don't have to enter in viscosity. You don't have, what I'm saying is you don't have to put viscosity into your components. It calculates viscosity from the parameters you enter.
All gas properties are a function of temperature, pressure, and composition. And so when I'm calculating pseudopressure, it's actually got to calculate all the way along in pseudopressure here. It's got to calculate the gas to the viscosity, but the calls are the same. So it's subcalling viscosity and it's subcalling Z. Because the inputs are the same.
I get it.
So that's why in the VB, you don't see that it's using viscosity. But here it is, M of P is pseudopressure. Here's the Z function, and here's the gas viscosity function. So here is the equation. It's going through a loop 20 times and calculating and sampling at 20 different places. It's using brute force to calculate this integral in equation 621.
I get it. I was thinking, since you were able to, since you calculated it in the sheet, I was looking at a situation where you called it, but I couldn't find it. So that was how I was concerned. But I get it now.
Okay.
Thanks.
And I pretty much stick with the viscosity that I get from this package that I got from what used to be on our calculators. You might remember the first class period. We used to have calculators that calculated all these correlations. And I think the textbook actually uses a different, there's two very popular gas viscosity correlations. And the one my VB uses is slightly different than the one the textbook uses. And so I'm not going to always match the viscosity that's in some of the problems and some of the pseudopressures that uses the viscosity. But we'll find that it only generates a small error. Okay, we're in chapter 6. We made it. Let's look at example 6.1. Oh, I don't have my data here. I'll get it here in a second. It's on the next page. I thought. Here we go. Example 6.1. So we're going to spend a lot of time doing this one problem. And let's go to the end. Of course, I got a lot of junk in here. This is, we'll call this example 6.1. I'm going to give you some more software for chapter 6 and 7, but we already know that we can merge software. But I don't think we need much software to do this 6.1. want to go grab that other one I had. What do we do, 1.3? No. Is this the one we've been doing? This is, I know, move or copy, create a copy. Okay, now I got these right next to each other. I don't know if I have all these things here, but let's see what I do have. I'm just trying to save myself a little bit of time. Do we have a gravity of the well stream? We do. It's 0.7. Now in chapter 6 and in chapter 9, we're typically given a well stream gas gravity. But that doesn't mean on your test for chapter 6 that you won't be given separator gas gravity and liquid yield and properties of the stock tank liquid. Are we told initial pressure? We're not. Our temperature is 200 degrees. H is 19 feet. Total system compressibility. We're going to spend some time right now, right here. Is 73.3, 10 to the minus 6. Now, how come I'm not told initial pressure? Oh, I know. We are. I'm sorry, we are. I got to get it from this other slide here. Okay, so we're testing a well. We have a pressure gauge in the well, and at time 0, we have initial reservoir pressure because we haven't produced anything. You see the rate on that top line is 0. So we do have an initial pressure. It's under the column of the wellbore flowing because most of the numbers in that column are flowing wellbore pressures. But at time 0, the well is shut in, so the initial pressure is 6180. Okay, then we're going to flow test this well. At 6 hours, our bottom well flowing pressure is 566 pounds, and we're producing 2.7 million cubic feet a day. At 8 hours, our bottom well flowing pressure is up a little bit, and our rate's down a little bit to 2.6 million cubic feet a day. What?
Based on reading this question, what told you that we were at? Oh, it's just because it's initial.
Yeah. Okay, I've just completed this well, and this is the data I've gotten from the field. At time 0, before I started flowing the well, my gauge was reading 6180. So basically that's my initial pressure. Okay, so I got initial pressure and temperature, and I got the well stream gas gravity, and I'm going to go to the trouble, as I recommended that you all do, is type in N2, CO2, and H2S, and for this problem there's zeros. But in the next problem, and in order to make this a pretty good template, when our VB functions call for those, address those cells so that if I change those, I can be more useful. I don't have to edit my VB functions. Okay, so I've gotten this information, but I've just worked this problem, so what I really want to calculate from fluid properties is not my total system compressibility, but my, we talked about it tonight, my gas compressibility. Okay, do I have the wherewithal to calculate my gas compressibility? Yes or no? Okay, and how do I do that?
Function.
What's the next keystroke going to be?
Equals?
Equals, very good. What's the next keystroke going to be?
C?
C. And there it is, gas compressibility. And then if I click my f of x box up here, it will invoke the dialog window. Pressure. Already thinking ahead, knowing that all my fluid property functions are have the same variables in the same order. All I have to do is change the spelling if I want a different one. I'm going to F4 that. Temperature. Temperature's never going to change. Gravity, never going to change. N2, F4. CO2, F4. And don't forget, there's always nothing left after the dialog box ends. F4. So now I got my gas compressibility.
Can you enlarge your zoom in?
Yes, I'll zoom in. Nice and clean. See, my gas compressibility is a function of everything I got up there. Now, what is the relationship between gas compressibility and total system compressibility?
It's one part of it.
It is one part of it.
One part of the three. You have formation,
Yeah?
gas, and then liquid.
Gas and liquid. Do those gas and liquids have any coefficients? And water.
You have to nice specific gravity.
What are the coefficients for those compressibility?
Saturation.
Huh?
Saturation.
Saturations. And in general, does the liquid and the formation compressibility contribute to the total? No.
Not very much.
So it's simplified to what?
It's Ng times Cg.
Okay, so here's a good test question. What's the gas saturation? With the information with the information I have right now, I can calculate it. They told me total compressibility is given in the problem. With the PVT data, I can calculate the gas saturation. So CT is bigger than CG. So gas saturation is CT divided by CG. Let's put it in percent. It's 88%. If I accept that these are negligible. Why would I want to know what the gas and water saturations are? You don't know the answer to this one. When I'm doing testing of a well, I not only want its deliverability, but sometimes it finds the outer boundary. If I find the outer boundary in a well test, I get a radius of investigation. And with the radius of investigation, I can calculate my area. And if I ran a log on this well, I know what my porosity is. And with my fluid properties, I got my formation volume factor, so I can calculate original gas in place, knowing the water saturation. Just some information I gleaned from the input combined with utilizing my PVT properties. What's the water saturation? 1 minus. Oops. All right. There's some more significant digits in there, but I'm just going to ignore them for right now. We're not going to use those right away. But the accuracy is there. All right. We don't know the area. We could calculate Z, ZI. I'm thinking we're not going to use it right away, but what the heck? It's got the same flavor as this. All I got to do is change the spelling from CG to Z, and I got my initial Z factor. If I want P over ZI, which would be the y-intercept of my P over Z cum or material balance plot, it'd be PI over ZI. If I wanted B sub G, I think I call it gas B sub G.
What did you just do to get Z?
Who asked the question?
Me. What did you just do to get Z?
I copied and pasted compressibility equation because I F4'd all the values, so it's calling the same values. I changed the spelling of the function from CG to Z. With me, it's all about the least number of keystrokes. I could have invoked it directly and said equals Z, and then I could have been prompted for the same numbers, but I already had all those numbers in there. You want me to do it again the long way?
Yes, please. Not even the long way, just do what you did. You said really quick.
I calculated my gas compressibility function,
Oh, okay.
not CT. You got it now, don't you?
Yeah.
Okay, I control Z. I couldn't calculate my CT was a value.
Mm-hmm.
It was given in the problem.
Gotcha.
Okay.
Thank you.
Let me zoom out for a second, see where I am. Basically, on this test, we're after perm and skin. I'll go over skin when we get to that point. Basically, we're after on any test is permeability. Where's my shapes? I'm going to learn Office 2013 here soon. Where are my insert shapes? Here we are. Permeability, that's what we're going to be after. And basically, any transient data hopefully will give us permeability. So we have some transient data. We have performance data. We turn this well on and we measure some rates against some various pressures. And so hopefully we can determine permeability. If we can determine permeability, then we can use that permeability to do long-term forecasting for the well. Okay, let's get table 6.2 in my spreadsheet. I'm not going to type in PA well flowing. I'm going to talk about that and we're going to calculate it. It'll be a little bit different. Let's just get the raw data in. I hope you're typing this in. A lot of these have a lot of data to put in, but this one doesn't have too much, so we're just going to do it by hand. Some of these other examples, I'm going to upload you the spreadsheet with 30 data points. What did I do wrong? I forgot 832, didn't I? Okay, so that's the performance data of the well. Everybody should get a physical concept of it. I turned on the well, and these are the rates it delivered at these pressures, again, at those different times. Okay, I'm going to calculate pseudo pressure. What's going to happen to my box down here? Okay. Knowing that CG already has everything F4, I'm going to copy, paste it, and change the spelling to Emma P. And I get that big large number for pseudo pressure. Now, it's the right number, but it's for the wrong reason. Because I'm actually calculating reservoir pressure for this 680, and I really want to calculate it for that 680 so that when I copy it down, it'll be the same. What else do I have to do with that formula?
One dollar from there.
I got to get rid of the F force on pressure, which is F. Now I'm ready to tap the corner of the box. Okay, now I got pseudo pressures at all times. Pseudo pressure of the well flowing. Yeah.
Something I should know, but pseudo pressure, is that in PSI A or is it unit?
Okay, how come I'm not here where I wanted? I thought I was. It's the integral of pressure dP, so it's going to have P squared. So it's going to be PSI squared. Z doesn't have any units. Viscosity has units of centipoise, so it's PSI squared per centipoise are the units of pseudo pressure. you even told me they're PSIA. Sometimes they don't tell you. Okay, I'm going to give away a secret. There's only one difference between Chapter 6 and Chapter 9. All the equations in Chapter 6 have well test units. They're hours. When we go to Chapter 9, all the equations are going to have production rate time units of days. Some of the equations are exactly the same, but they'll have a different coefficient. You'll go, why? All your well test analysis are in hours. All your production analysis are done in days. So let's see here. We want to build a plot. It should look something like this. Figure 6.12 on page 118 of your textbook. Those are our 4 test rate data. So we've got to build a time rate function. And we're going to, off here to the left, we have variable rate production history. Is that what we have? We have, at different times we have different rates. We also have different pressures, but we have different rates. So we're going to solve equation 649. We're going to do this summation here. And I propose Q sub j minus the previous rate times the that final rate. I propose that we put this in the visual basic function because it's a summation, it's a loop. And although we can work this out, oops, I'm moving too fast. Where am I? Here's the summation done out, and you see we would have to do all these steps in different cells. And that's just for at t equals 9.5 hours. Now, if I had instead of 4, let me show you what's going to happen. Is the number of terms increases in this calculation. The first one's easy. We have 4. Then you have 2 things you add together. And then you have 3, etc. So if you have 100, you have an awful lot of calculations in there. And it's so much easier just to send this array into a VB function. It's only like 5 lines of code. So I think that that's what we'll do. So we have to calculate this rate time function. But before we get there, we got 3 things we're going to knock out. We're going to look at pseudo pressure, which is not the way the textbook solved this problem. They solved this problem with apparent pressure. Now, all you really need to do before the next class is read all of Chapter 6. Well, not before the next class. Next class is a test. Before the class after that is read all of Chapter 6 up to example 1. And then you'll understand everything that I'm talking about. And then we can proceed pretty rapidly thereafter. We're going to solve this with apparent pressure and pseudo pressure, and we have to knock off this superposition function. Then we'll easily calculate this so you don't have to do it manually. actually, he calls it the time rate function, doesn't he? Pressure function. What does he call this? Pressure function, that's PSI per MCF, time rate function. That didn't work. I'll just leave it like that. So we're going to get something other than 6 hours. And as a comparison, I'll kind of get this topic over, but in transient pressure analysis, it just so happens that we use the log function a lot versus time, because in radial flow, the shape of the vortex is such that it becomes linear if we take the logarithm of the radius. We're also going to look at linear flow, and the time transformation will be dominated by the square root of time. So throughout Chapter 6 and throughout Chapter 9, we're going to be doing two major time transformations: logarithms and square roots. Let's just look, if we didn't use the superposition function, what the logs will look like. That's the log of time in hours. Well, test units are hours. Now we're going to come up with some numbers that are similar to this, and we can see them down here. I can't move this around. Time rate function starts at 0.77, ends at 1.2, 0.7. The first number is the same. 0.7782 is the same because there's only one number in that calculation. It's only when the second and when we have a rate change do we have two calculations. So this 0.7782 is exactly the same as this 0.7782. So my first time function, even though it is, where's my equation? Move too fast again. It's got that little header with the, yeah, right here. So even though we're doing the summation function equation 6.49, when n is equal to 1, it just resolves to the log of time. There is no loop. Once we get some of these calculated out, it'll make some more sense. So let's see if I think my spreadsheet already has this. So I thought it did. Oh no, that's right. So I'm gonna import them. I don't have to write mine. I'll just show you mine, and then you guys can copy it in. What's this? SBB. Oh, I'm not there yet. Okay, that's all you got to type in. I guarantee, once you do that, it'll be much easier than trying to do it in the spreadsheet. That's all there is to the function. So it's going to take in two arrays, the time array and the rate array. And then it's going to put out an array that's going to have the time function. And although, even with 4 variables, or 4 codes, I can still type this code in faster than doing the equation. And if you have 100, I guarantee I can beat you. Okay? So, what you probably want to do is do File. I want to add a module. Right here. Right here. Insert a module. When you insert a module, it'll be called Module 1. And if your Properties window's open, you can rename your Module 1 Superposition. If your Property Windows is not open, hit View and hit Properties window. You don't want to be having modules named Modules 1, 2, 3, and 4 because you'll never know what they are. So create a module, call it Superposition, and then type in these lines of code.
We can't see.
You can't see it? I think I can increase the font.
You can make a snip tool and make it bigger in the Word.
What?
You can use a snip tool to copy this code.
If I copy the code, you're going to lose the color, but that's fine.
No, I mean.
No, he's saying use the snipper to take a picture of it and then just.
Snipping tool.
I get her.
You mean like this, like I've been doing? How's that? The first line of code is going to count the size of my array. In this case, it's going to be 4. And then it's going to do j equals 1 through 4. And then at some point in time, you'll recognize that that's the same equation as whatever it was in our textbook, 6.59. And so it's a for loop for j equals 1 to n. This is how I keep you awake in this class. And the reason I bother to give it the term radial, superposition for radial flow, is I know that this logarithm of time, this time transformation for almost all radial flow problems is going to be a logarithmic transformation. You'll see it over and over again as we go through the chapter. How many people got it done? Okay, I'll flash this back up if you didn't get it done, and maybe have students come around and help. So I now have that Visual Basic function in my spreadsheet, and I can invoke it. What is it called? Super something? Super radial. What happened there? It wants to know the time array. And then I don't know why I got a decimal point there. It wants to know the rate array. And something is wrong here because my prompt's not right and that first number's not right. T is a variant. It should be prompt for T and Q. Oh, I know what I'm doing wrong here. Isn't that my last number? Yeah, 1.1819. Now, here's where I have to be clever. I actually got the right number for the last answer. 1.1818. 1.1819. Okay, see, I got the same number as the last number on the table. Now, this is where I have to be really clever. This gives me that I'm going to go up and edit my formula bar. Always from E4, the top, I'm going to F4 that. Always from G4, I'm going to F4 that. See how it's going to always start there and end where I am currently. And then if I copy this up, I'm going to do this one at a time. 10287. Oh, 10287. See, I got the right number? That's because you see, it only has the information to that point in time. It's the array from always the same start. That's why I F4'd the start of both the arrays, but it's relative to the end point of the arrays. Okay, do you see what's F4'd and what's not F4'd? And now it's basically, it's always been ready now to copy all the way up. So 7782 is my first number, 9271 is my second number. So I'm telling you, Visual Basic will save so much of your time. Yeah, so anytime I click on a cell and look at the formula bar, it should have it should highlight the data to that point. If I would have done this manually, I would have had to do it one at a time because it would all had a different array. I would have said, the only thing I have is this time and this rate. I still don't know why I get that. I'm going to get that number. But if I copy that down here, I have to make it for that and that. That'd be the manual way to do that. See that? Then I get the 9271. But to do it automatically, I just got to make sure that I anchor back to the first point and make it relative to the last line, and then I can copy up and down.
Is that what we just did there? Is that supposed to be a full representation of equation 6.49 or just a part of it?
Oops. It's the summation. We are going to cross plot a delta pressure divided by rate. We almost have those terms in our
Oh, okay. That last term's outside the summation.
Yeah.
Okay.
And then what we're after is that slope of that straight line. Once we get the slope of that straight line, that's going to be proportional to permeability. So it's the summation term that I'm doing in the formula. J equals 1 to n. And you see, when I have 2 data points, n is 2. When I have 3 data points, n is equal to 3. N changes as I add data. But j equals 1 is always the same line. Yeah.
Maybe this would be a good time for a break. People to catch up.
Okay, that's a good idea. I'll flash up the VB in case you missed it. You know what you're supposed to get. I matched the book answers exactly. Because there's no correlations involved. It's just a straight summation. So, and then I will put the PowerPoint of the VB. I'm going to crop this a little bit more, slide it up, so that it's more at the top of the room. But before that, I'm going to pause my recording. Okay? I thought I brought a water down here, but it didn't look like I did. I must have forgotten. I'm going to go all the way back to my office and get a water.
We can go start from the bottom of the top. This one? And this person?
Oh, you can't get anything to work out down there? Work.
Can you go back to the spreadsheet?
I can't right now. But the answers are in the book. Where's your- let's see. I think where it's going. Okay, you get the full prompt. Do you get a number here?
No, I always get the value when we don't provide it. References the right cells and everything.
Oh, the zero? Yeah. This one?
I'm telling, I know what the problem is. You didn't put anything in for H2S. You didn't scroll down. You didn't scroll down.
Okay.
See, you thought you were done, but you're not. You're not done till you put in something further. So put in H2S. E3, let me look at your last one. Click on the formula bar for seconds. Oh, so you must have typed something in, must be a different problem. Didn't get there. Why do you get 5?
Can you click here to see what it says? So go for last one to your
Oh, I bet you know which one. Get rid of the 0. Get rid of the first one. Get rid of the, change your boxes. Change your boxes. Let's get rid of it. That box looks like this. Shrink it to here. by changing the corner of the box with your mouse. There you go, do the same thing. E4, yeah, change that 3 to a 4. Not that one. The first one. G3, just make that G4. Okay, now hit enter.
Yours work?
Make that. You gotta make that box bigger. Can't you do it, but
We shouldn't have this P3G7 right on. We've got too many.
E4 to E7, G, oh yeah, G4 to G7, yeah.
We don't have that.
And then I was just on the phone.
There you go.
Thank you.
Should we have copied that?
Don't get me wrong.
Okay. What do you guys want? Spreadsheet?
So for the first one, you say, the second one,
Who asked for that?
you go. Yeah, fine. Yeah, we do.
But what? Okay, go back to your spreadsheet.
How I did it, I started from the last one because I had to fix it. Like first, I just took all of them, and then I started to fix it up. Like, you know, so I already learned from the last one, and then just take all of them and see what happens. But it shows in the list of the different options, right? Okay, I closed it now. Yeah, that's what yeah, that's what so now for the second one. You want to just
It doesn't make it out of the loop. It has something like a zero divide. Yeah. I don't know how many times it's making.
oh, I know. Yeah, because because when you start from the back, you take all of them. So in this case, I think you said you start from bottom to from here to
No. If you divide by zero, it's going to be bad. It couldn't get anything. I don't know what's wrong with your function.
so now.
You see, it calculates, it gets here, it works fine. Goes fast as it moves. It gets here. You see, it calculates that. It knows that, knows that, it knows that. Knows that number. Knows that. But somewhere before it gets done with it, you can't make it all the way through the loop. What I can't understand really is why can't it make it through the easiest case? I don't understand why it can't make it through the easiest case. It should just give me the log of 6. I can't tell you. I can't solve other people's problems. So I would just, I can't take any class time at this point right now to fix your problem.
Okay.
I don't know, I'm exhausted with things I can try. You may have to drop the class. I'm sure there's something that can be fixed, as your other VP functions are working. I just don't want to know what it is. Okay, how are we all doing? Well, I gotta hit record. Okay, so we got a rate time function, right? Other than one person, does everybody else have the rate time function?
Mine's not working.
Why isn't it? Are you getting values or you're getting numbers? Okay, the only one problem that I saw at least one student have is, I shouldn't have done that, is you don't want to have the first line. The first line of code that it should grab is the 6 hours of the 2711 rate. You don't grab 0 and 0.
Yeah, I didn't do that.
Okay, one student did that. So that was just a problem invoking the function. You can't get 7782.
Yeah, I don't know. I've looked at the typing 100 times.
The other common example is some people spell this word. Are you getting zeros or values?
No value at all.
Pardon?
No value.
You're getting the word value.
I'm getting
This word has to be spelled exactly the same as that word.
it says number, name, question mark.
Okay, sometimes it thinks these are labels. one thing I can do to make sure that that's not a label and it's really a number is I divide it by 2. If I can do that on my numbers, then it's not thinking it's a label. It knows it's a number. Sometimes columns get set up because they think they're labels instead of numbers. Can you divide all your numbers?
Yep.
So it's taking in numbers in. I don't know, one thing I'm not very good at is debugging other people's work. I can debug my own work when I write it, but maybe for some more optimism, how many people got the right numbers? Oh, see? So I can see the pass-fail list already. Okay. We've not 1/3 of what we want to get done. I'm going to calculate pseudo.
Why don't you calculate it in again?
Huh? Did I already do it?
Yeah, I thought we did.
I'm sorry. I'm going to calculate P apparent. Isn't that what they call it? I'm going to go back and I'm going to check what the book has. They call it normalized. And refers to normalized value. They're going to use normalized value. I'm basically going to do equation 623. 1/2 of the integral from 0 to p of p over dp over mu z is my pseudo pressure. Or I mean 2 times that. When I multiply by 1/2, well, basically I have pseudo pressure. I'm going to multiply it by 1/2, and I'm going to multiply it by viscosity, z factor, and pressure, subscript r for reference, which is at, in this case, average reservoir pressure, original reservoir pressure. So I need this product here, 1/2 mu z over p. We don't have a viscosity, do we? Or did they give us one? They gave us one. I haven't put it in yet. I'm going to use their viscosity. Let's just take some time and put in their viscosity and calculate as ours and see what the difference is. We're going to use theirs eventually. It's 0.0286. And if I were to calculate viscosity, I change that m to u and I get the viscosity. And it's different. Let's see what the relative error is. Almost 7% off. Okay? Now, this is not going to have a huge impact on our final result, but normally I would use my viscosity so everything was consistent. But so I want to match some of the numbers in their book. I'm going to use their viscosity. So what are we looking for? We're looking for 1/2 mu z over p. And that's going to be some small number that when I multiply by pseudopressure, and it's not apparent, is it? It's normalized. Isn't that right? Did I subscript that? Doesn't look like it. Pressure normalized. So I just take my pseudopressure and multiply it by my constant. And it should be a number that looks on the order of pressures. And did I make that absolute? I did. I can do it for my initial pressure.
Which constant?
My constant, I'm going to call it my P norm constant.
Can you show us how to get that constant number?
That constant number?
Yeah.
Can you zoom in again, please?
I paid attention to the textbook. It says that my normalized number is my normalized number is my pseudopressure times 1/2 mu Z over P. Reference. R here is for reference. And again, this is part of the reading all the way up to example 6.1. So I like you to get through 6.1, but then get all the reading done through 6.1 so you have a full understanding of all the concepts used here. So I don't like normalized pressure. We'll see why here in a minute, but we're just going to do it. It's because some engineers don't like big numbers, like pseudopressure. And so they want to normalize it. You see how those numbers have the same magnitude of pressures. And because my viscosity function is different, although you see this, their 4709 becomes a 4455. Their 66 becomes my 62. Their 142 was 13. So you can see I'm order of magnitude, I'm the same number, but I'm different. And that's because my pseudopressure uses a different viscosity function than the textbook likes to use. So my pseudopressures and my my normal pressures are not going to match exactly. Be patient with me. We're going to be getting the slope of a trend. And as long as those errors are consistent, I'm going to get the same result. Okay, so I got my time pressure. He calls it PA, but in the textbook he calls it normalized. Now my pressure function is just delta apparent pressure divided by Q. He calls that his pressure function. Okay, everybody with me?
No.
I got that.
We're trying to get these numbers. Let me zoom in just a little bit. And all I'm doing is multiplying my pseudopressure times a constant.
And that constant you got from that equation right there, but what was your reference pressure?
Initial pressure.
The
Okay.
60, the 6-1.
So I got mu GI, ZI, PI. I use the viscosity given rather than the one I calculated. But that relative error of 7% is why I can't match their other numbers, because remember, viscosity is built into my pseudo pressure calculation. I don't use the textbook's viscosity correlation. I use the one that comes in that package because it's consistent. But if I were to cross plot his numbers versus mine, I'd have a linear trend. See, my big numbers are big, and I'm basically kind of a percent error off because of my viscosity correlation. But I'm going to end up cross plotting these numbers and only be interested in the slope. So that this difference in these numbers are not going to be that big of a deal. When we're all done here, before we leave class tonight, we're going to decide that we don't need to do this, so it's not critical, because we can just do it with pseudo pressure. This is just to make some people feel comfortable, because the numbers are less than 10,000, where the pseudo pressure numbers are bigger than 10,000. They don't like to look at numbers that big.
So when you calculated your pressure pairing here, you're just doing that even though it was already actually given to us?
Yeah. And then we're not going to use it later. Okay? But I want you to be on board with the development.
Okay.
If I would have had their viscosity correlation, I would have matched their numbers. I can't match their numbers because I don't have their viscosity correlation.
Okay.
The books in my Z's calculate right. My integration's the same. It's that viscosity throughout this textbook is going to be slightly different. The other important message here is that normalized pressure and pseudo pressure are linearly related. We just multiply them by a constant, right? So the slope that we get from a normalized pressure and the slope we get from pseudo pressure are going to be the same. So we never have to go here. But I'm doing it for completeness so that we can see how this first example is completely done. Okay, I'm going to move on. We're going to get the pressure function. Remember when I showed the PowerPoint, my animation shows how the delta pressure, delta pseudo pressure is that driving force. That's how we got that 45% error if we use the wrong gas gravity. Now we're going to actually use that delta pressure. It's equal to initial pressure. Here we're using normalized pressure. I'm going to F4 it because it's never going to change. And I'm going to subtract the pressure on that line, relative, and I'm going to divide it by rate that's on that line. The rate is 2711. Okay? Now these numbers, again, won't match exactly. Their rate time function, their pressure function is 1.7, and I got 1.6. I think this is ready to tap down, and I can't, well, I can't, yes, I can. I can do this. All I got to do is make this table a little bit smaller. There we go. So here's my numbers, and their rate time function, pressure function goes from 1.7, 1.75, 1.77, 1.8, and mine are all a little bit smaller. Because my normalized pressures are different, because my pseudo pressures are different, because I'm using a different viscosity correlation. Let's just keep moving. Now I have all the data I need to make the plot that I've been asked to do.
Sorry, that was your initial pressure time for normalized, that was your rate?
Yeah, delta pressure, so I'm already trying to jump ahead and say delta pseudo pressure. Delta normalized pressure divided by the rate. The leading term of the delta pressure is initial pressure minus the pressure at that time for that flow rate. Okay, so now we're going to create figure 612, the rate time function versus the pressure function. I hit the control button to get two things. and I insert chart and scatter. Okay, now let's look at the textbook and see what he's going from 0 to 1.4 and 1.4 to 1.9. One more time, Joe. Y-axis is 1.4 to 1.9. Okay, then my graph right here should just look just like the textbook. Oops, I keep doing that. Right? Looks pretty much like it. In fact, I can do my interpretation automatically with the trend line, right?
You're graphing delta P against what?
Pardon?
You're graphing delta P and against what? What is that?
I'm plotting just like the textbook says, time rate function versus pressure function. And of course, there's 100 ways to instigate that graph. But the way I normally graph two numbers, as long as the first one I want is on the, as long as the x-axis is in a column previous to the y-axis, I can just do it by highlighting it, holding the control button down, and then highlighting the x. And then I can go right to insert, chart, scatter graph. Okay? Then all I did to get from there to here, to make it look more like the textbook, is I didn't use the default min and max for the y-axis. I used the exact min max that the textbook used. I'm going to format my trend line, make sure it gives me my display, my stuff here. So I'm going to need this slope. Now, in general, when I'm going to calculate numbers, I don't want to rewrite down something that's on the graph. I'm going to find a little spot in here. I'm going to move things around here a little bit. I'm going to put their CT on top of my CG. We haven't had to use H and porosity yet. Did we get a porosity? Where's our problem statement? Porosity is 17.6%. Okay, I want the slope. All I'm going to do tonight is get the slope and the perm. All right? We get these things and we can go home. Now, I can see my slope. It's 0.2138. Let's see how we did with the textbook. I don't know why I keep doing that. They got 0.236. And if I want this slope, I can just say equals slope. That's a built-in VB function. Known y's is my pressure function. Known x's are my time rate function. And see, now I have the same number in my spreadsheet that appears in my trend line, 0.2138. Does everybody get that? Okay. My trend line automatically does a least squared linear fit of that, which is what I want. And if I ask it to, it'll tell me the equation and the regression coefficient. Okay? So the slope is 0.2138. I want that number in my spreadsheet. I don't want to copy it down because when I change my data, I don't want to have to recopy it down. So that slope is just the slope of those known y's and those known x's. I'm not going to really need it, but I also eventually want to know the intercept. And I have a VB function built in for that to intercept. But I can do my same trick. It takes the same data. If I F4 my data and copy this down and change the spelling from slope to intercept, I can get the 1.45 intercept with the textbook given. 1.532. Okay, now I get K. I think we're going to need a B sub G. Let's look at our equation for K that we're going to use. It's right here. Equation 650. Here's the equation that we're going to... Can I copy that?
Take a picture of it.
Well, can I do it right here?
Well, if you go to,
What happens when I do this? It didn't work. You knew that.
go to edit, take snapshot. And just highlight it like that. Just go back and hit Control D now.
See, this is why I keep teaching. I can learn stuff. Voila.
So I'm going to do that.
Yeah, it wasn't really bad.
Side 12.
That's where we're headed. M is the slope. M prime is my slope. Now, we got kind of a messy B sub G. We're going to have to spend 3 minutes here on B sub G. You ready? Raise your hand if you're ready to do B sub G. Okay. Let's do B sub G my way. We haven't already done it, have we?
I thought we did.
I thought we did too.
0.0.
Where is it?
Under P idea.
No.
There. Oh, no, we didn't. It's
Okay. Equals gas BG. And I think we changed yours in class at one point in time. But anyway, mine's prompting this way. 618. Temperature's 200, gas gravity's 0.7, 0. And this is the trouble a lot of people have. They think they're done, but they need to scroll down and get the last number in. Okay. So that's in reservoir volume per standard volume. It could be reservoir barrels per stock tank barrels or reservoir cubic feet per standard cubic feet. Okay, it's a dimensionless term. It's reservoir volume per standard volume in whatever units you want. But this equation is a rollover from the oil field equation, because originally we all did oil wells and the only thing we had a permeability equation was for oil. So I need a B sub G that will take my MCF and convert it to reservoir barrels. Again, we'll get rid of normalized pressure, we'll get rid of this funky B sub G, and we'll just use pseudo pressure. And we'll see that it's a lot more straightforward. So we need a B sub G in their units. We need B sub G in units of, then we'll compare. We need B sub G and reservoir barrels per MCF.
So you just divide by 5.615, right, times 1,000.
We got 1,000 in here too. So I'm going to call that reservoir cubic feet per MCF per SCF.
Reservoir cubic feet.
Per standard cubic feet. That's what I just calculated. But now I want to convert my number to their units. I got to divide by 5.6. And to get it to MCF, there's 1,000 MCF, so I got to multiply by 1,000, and then I should get a number close to what they got. That I do 58778. And there's no viscosity in here, so it'll be very, very close. So let's just use my number. Forget the fact that they didn't give us a number. 5827 versus 58778. Okay?
Sorry, could you go
Huh?
with that conversion one more time? Step on.
I divided by 5.61458. In fact, I think I have a equals cubic. I do. Cubic feet per barrel. $5.61458. I should have used the real number, so I don't have to type in an approximation. And then I multiply by 1,000 because instead of reservoir volume per standard volume, I want a reservoir volume per 1,000. Because my rates are in MCF a day, they're not in standard cubic feet a day. Okay, now I think I'm ready to calculate K. I got 162.6, I got B sub G. There's a bar over it for average reservoir pressure, but this is a reservoir at initial conditions, and so we're saying average reservoir pressure is initial pressure. So my B sub GI is going to be their B sub G bar. Now, where B sub G bar is more applicable is if my reservoir is halfway depleted and I shut it in and get its current reservoir pressure, I would no longer use PI. But this is a new discovery well. The initial reservoir pressure is the average reservoir pressure.
In a case like that, would your average, I guess, would your average be your initial and then where you're at? Just those two? Or would you actually have to do like a step and incremental?
That's what I'm trying to explain.
Incremental step.
That bar means your average reservoir pressure. Average reservoir pressure is defined. Average reservoir pressure is the pressure that will be in the reservoir everywhere if it's shut in for an infinite amount of time.
Okay.
It's that dotted line that I put across the vortex. Okay. But initially, it's initial reservoir pressure.
Right.
We haven't drawn out in a 6 to 9 hour test enough to even make a tenth of a pound of difference.
Okay.
Okay?
So we're talking days, weeks, months, years?
But on that P over Z plot, if I go down 10 years from now and run this kind of analysis, I don't use initial pressure. I'm using average reservoir pressure. But this is the first test run on a new well. So average reservoir pressure is initial pressure.
Okay.
Okay, same with mu G. Mu G, we're just going to use mu GI. We've got M and we've got H. Let's see, we got everything above there. So I can calculate K. It's equal 162.6 times B sub G with their oil, I call them oil units because they're reservoir barrels per MCF, times mu sub G. There's no difference between gas and oil. They're all measured in centipoise. Divided by the slope that we got, and divided by the H, the formation thickness. How did we do? How did we do? I got 0.67 and the textbook got 0.61.
0.65. Yep, 65. I think all of our numbers are really good.
Did I make a mistake in my spreadsheet?
Yeah, the pressure, that's the pressure. The last one pressure should be 46, 1646, not 56.
On my table?
Yeah, PWF. PWF.
Is what?
Yeah, 46. 1646.
All right. So I get 0.65 from my current.
Yep.
Okay. Now, we can use a different equation than this one. And we can plot pseudo pressure versus our time function. In which case, we have the equation. We don't have rate in our equation because it's built into the slope. It'll be just 1637 T over MH. But I'll pick up there. I got to have something to do, and I'll calculate the skin next week. But I'm kind of out of time. That's right where I'm going to leave off. We're going to calculate skin. And I feel like I really want, no, not next week. Next week we have a test. And let's talk about this for a second because I hate to lose the teaching time. I'm not going to give you a 3-hour test. Okay, the test will be an hour test that there'll be a bell-shaped curve for the people that finish it. Some people will finish it in 40 minutes and some people will finish it in an hour and 10 or 20 minutes. See what I'm saying? But no one's going to take more than an hour and a half. So I don't want to lose an hour and a half of lecture just to give an hour test. That's the only problem with an evening course. The final exam's a little bit different. You know, you guys probably spend the whole 3 hours. But for this first test, I only want to use the half the test. Do you want the first half or the last half? First half. Okay, so here's the way it'll work. I'll give you a test. You have an hour and a half to do it. It will be an hour test. You'll have an hour and a half to do it. And then at 7:30, we'll come back in here and we'll finish this. So if you may have time to go over to Starbucks, okay, if you finish the test quickly. Yes?
Do we use our own spreadsheet on that, the one we've been developing the test, or you're going to give us a spreadsheet?
I'm not going to give you anything. I'll give you some problems.
So we'll be able to use a computer?
Yes, yes. On this first test, you'll be able to use a computer. Not all tests. You may come in here expecting to use your computer, and I'll just say, I'm going to have a short answer test. Okay. But on this first one, it's definitely going to be computational. I want you to be on board with the calculations. And I think no one's having any trouble with the VB functions before the ones we wrote today. Okay?
Are we supposed to write VB functions in the test?
No. You will not have to write VB functions on the test. Because there's so many things that could go wrong that I can't.
That'd be really cruel.
Yeah, that'd be cruel. Yeah. My director would be in my office the next morning. What'd you make them do? No. Typically, I will give you Visual Basic. Occasionally, if there's only one thing to add, and it's like 5 or 6 lines of code, I'll make you write a class because it keeps everybody awake. Okay, any other questions? Yes?
The last part of chapter 1 is talking about water and oil.
Water and oil. Don't worry about the water. Don't worry about the oil.
What about the...
Sir mentioned the same with like Sutton's mixing laws and Stewart mixing laws.
No.
Don't worry about it.
No. You know, all that stuff's going to be given to you. You're never going to have to make that calculation. It's fundamental. It's stuff I used to teach, but I like to spend the time on these dynamics. And once we start getting into 6 and 9, it's a lot more fun.
So are those like corrections included in your functions? Like, you know, because like whenever we have like contamination or we have a sour gas, then we're going to have a percentage of H2S.
Let's just do a sour gas right now. 10% H2S. What am I going to type in? What's the first thing my finger's going to hit?
0.
No. 1. What's the second thing my finger's going to hit?
0.
Yes, because it's looking for whole percentage points. That's the most important thing. And if you look at the Visual Basic, the first thing it's going to do is divide that number by 100 and turn it into mole fraction. So don't put 0.1 and don't put 10%. Put the whole number 10. I've just changed my gas to a 10%. Let's see what the effect is on permeability. 0.65, 0.64. It's going to affect the numbers, okay? So I just did a sour gas example. And see, I was smart enough to actually have a cell for N2CO2 and H2S so I can quickly do that. And if I would have shortcutted it and put zeros in my VB calls, I wouldn't have known which ones had the zeros in and which ones didn't. Okay? We can handle impurities.
And are you going to provide us with a new sheet, or we're supposed to use the sheet?
I just use your sheet. Then you'll probably just transfer the answers to something or other. I haven't quite figured it out. I haven't written the test yet.
And for the gas turbulence and the flow coefficient?
The gas what?
Turbulence.
Oh, I haven't. Gas turbulence is in. Oh, there is something in Chapter 1 about turbulence. I don't usually deal much. I'm not going to ask you anything about turbulence. Maybe in a Chapter 6 test, I may ask you something about turbulence, but not in Chapter 1. What's it related to, though? Did you read about it?
Gas turbulence?
Yeah.
That flow?
What kind of flow?
You mean like turbulence?
Yeah, turbulent flow.
Near wellbore?
Near wellbore. What happens near the wellbore in radial flow?
Non-RCA.
Why?
Because the velocity of the gas increases.
It's the speed of the gas.
Yeah.
Okay? It's going through concentric circles, like the loops around Washington, D.C. And way out there, it's moving real slow. But it has to have the same mass rate out there near the wellbore, it's got to go at real high velocities. Do we have that problem with multi-frac horizontals? We don't have that big constriction. We're flowing into a big, huge area. In fact, many of those areas. So what used to be a big problem when we were dealing with low-hanging fruit, we don't have anymore. I don't really.
And not to contradict that at all, but in your fractures, is that ever an issue? And I just don't know. Do you have non-Darcy flow?
You get non-Darcy flow where you have bottlenecks. Multi-frac horizontals remove bottlenecks. End it on a note that has nothing to do with your next test or what I want you to do. Okay, so study for your test, and I think that reading this part about Chapter 6 will reinforce the principles from Chapter 1 that I want you to know. You should know that vocabulary after looking at 1. You should be able to read Chapter 6 up to the example 6.1 and understand what they're talking about. When they're talking about pseudopressure, porosity, and height, those are all the things we looked at in Chapter 1. So it should make Chapter 6 reading much easier. If you have a question, go back in Chapter 1 and look at it, and that'll help you study for the test. All I'm trying to get out of Chapter 1 is that be able to have the concepts down to be able to do Chapter 6 and 9. You got a question? No? Yes?
I lost track of you like right near the end, but I don't want to hold the whole class up. I thought if I could just kind of ask you from a certain point.
I'll turn off the recording.
And I have a question about one of the examples, like just curious, I don't know. So they said that, like for that example, they were going to ignore nitrogen, and they were like, yeah, I kind of want to show you this. Like they used the composition of the gas of another example, but they said they were going to ignore the nitrogen, but they still use the same gravity from the first example, but that's included the nitrogen. So the gravity will change a little bit.
But nitrogen has, what is the molecular weight of nitrogen?
16?
No. 14.
Isn't it very similar to that of methane?
That was like
It's-
14.
and methane is,
It's about
yeah. So if I can understand how the textbook is getting away with it. They couldn't do that with CO2 or H2S because the molecular weight is so much different. The gravity would have to change considerably. But
So they just like take a
they're close enough that you could say, based on the gravity and whether it had 8% or 12% nitrogen, wouldn't have a grave effect on the gas gravity. Okay, I'm going to turn up the recording.